Do. Elastic collision problem 12.3. Okay, so in 12.3, what we have is a 4.3 kilogram block, and it's sliding along a frictionless surface at a constant velocity of 6.2 meters per second in the positive direction. So it's a block. It's got a mass of 4.3 kils, and it's moving positive direction at 6.2 meters per second. It hits head on, so one dimension, another block that was stationary. After this collision, the stationary block is now moving at 4.3 meters per second. We have no idea what the first block's final velocity is. And we have no idea what the mass of the second block is. These are the things we're looking for. These two unknowns are what we're looking for. Now, if you've been following along with these videos and you've done problems 12.1 and 12.2, you'd know that at this point, for a perfectly elastic collision, we'd go ahead and write out a momentum equation to conserve momentum, which is something that always happens, and then we write out a conservation of energy equation, which happens in perfectly elastic collisions. However, in this specific problem, our second object is completely stationary. Okay, it's a stationary block. And what we can do then is we actually already have, through the magic of prior derivations someone has done, we actually have equations that give us some information here. We know that for our final velocity of the projectile, or the first block, we know that its equation is going to be its mass minus the second mass, that's the projectile minus the target, divided by their masses added together, multiplied by the velocity of the projectile, which in this case is the v1 initial. For our second object, the target, we have an equation for that too. We know the velocity of the target, so v2f, is going to equal 2 times the mass of the projectile, so that's the mass of the first block, divided by their masses added together, multiplied by the velocity of the projectile, which was the first block's initial velocity. These are two equations that we have for a stationary target. These are what I like to call the magic equations, because deriving them is a real pain in the butt, but that derivation has been done, so we have them. This derivation to get these does conserve momentum and conserves energy, and this is what we get from them. Luckily for us, we can plug some numbers into this setup. While we don't know what the initial or the first block's final velocity is, and we don't even know the direction yet, although we could think about it, we'll talk about that, we know some information. We know its mass is 4.3, well, that looks bad, 4.3 kilograms. But we don't know the mass of the second object. And if we divide, this will be 4.3 plus the mass of the second object. But we do know that projectile, or the first object's initial velocity. It was 6.2 meters per second. If we go to our second equation here, we can get some information about that. We happen to know that the final velocity of the secondary block was 4.3 meters per second. And it's going to be equal to 2 times the mass of the first block, which was 4.3 kilograms. We can divide that by 4.3 plus m2, because we don't know that mass, but we do know that the first object's initial velocity, or the projectile velocity, was 6.2. So looking at these two equations, we actually see something interesting. We have two unknown variables, m2 and v1f, but we have two equations to solve them. What we're going to do here is, if we look at the right, normally we'd use some sort of substitution method here, and we're technically doing that. But if we look at the right equation, we can solve this for m2. It's the only missing variable there. Once we find m2, we can just put it in to the other equation and solve for v1f. So this is actually a pretty straightforward thing to do. It's just a little bit of mathematics to do it, nothing too crazy. To do this, however, we'll start with this equation. What I need to do is I need to get this m2 into a numerator, which means I need to multiply both sides by this entire quantity. So when I do that, what's going to happen is I'm going to have 4.3 from initially multiplied by 4.3 plus m2. And this will mean that in a moment, I'm going to have to distribute that 4.3 onto both terms. But this is just going to be equal to 2 times 4.3 times 6.2. It's going to give some number. So if we go ahead and distribute those 4.3s throughout, 4.3 times 4.3 is 18.49 plus 4.3 m2, because we distributed. And this will equal 2 times 4.3 times 6.2, which is 53.32. Now to solve for m2, I need to get the m2s by itself. So I'll subtract by 18.49 on each side. That's an 8. So now I'm going to have 4.3 m2s equals 53.32 minus 18.49, which is 34.83. And I know I'm ignoring a lot of units here, which is never a super great thing. But I know I'm going to get kilograms back at the end. Because when I divide by 4.3 here, I have m2s by themselves, and everything is in an SI unit. So 34.83 divided by 4.3 is going to give me a mass of m2 of 8.1 kilograms. And thank goodness that came out to be a positive number, because the mass better be positive. If you got a negative answer there, you know you probably made an algebra mistake somewhere. It happens. Go back and find it. So now that we know what this m2 is, we can just, like I said, go back into this first equation and plug in 8.1s everywhere. So this equation now simply becomes v1f equals 4.3 minus 8.1 divided by 4.3 plus 8.1 times 6.2. You can't just cancel out the 8.1s here. These are terms that are added together and then divided, so be very careful about that. I know I've made that mistake before. So 4.3 minus 8.1 gives us negative 3.8. We divide that by 4.3 plus 8.1, which is 12.4. And then we're going to have to multiply by 6.2. So I'll put that in parentheses there. If I multiply and divide everything here, what we find for the first object's final velocity is it's going to be a negative number because of that negative. So 3.8 times 6.2 is 23.56 divided by 12.4 gives us the negative 1.9, and because it's a velocity in SI units, meters per second. Which is kind of interesting because this means that this object up here, it actually hit it hit and it bounced backwards, which we didn't know. Now, we could have predicted this. We could have predicted that M2, the 8.1, it did need to be greater than the 4.3. And we could have predicted that this object, the projectile here, bounced backwards after it hit. And the reason we could have predicted this is because we know that if we strike an object that is not moving and the masses are identical, the object that struck the moving object, the projectile, will stop, and the object that was stationary will gain all of that speed to conserve kinetic energy. This is what you see when you play pool. The cue ball stops, and the other ball, boop, moves ahead at its speed. In our case here, the second object didn't move forward at the full 6.2 meters per second. It went forward at a lesser speed, which means that it probably has more mass. You could also think of it this way. If this had a very, very small mass, like it was a ping pong ball, something very small, when it gets hit, it would dart away very, very quickly. It'd be faster than 6.2. So we knew that M2 had to be greater than M1 here. Because of this, we could also think about this as the fact that if M2 is greater than M1, then when they hit, this is like a small object hitting a big object, which means that it's going to have to bounce back off of it. It's not going to be able to push through it. It's going to bounce off. So just by that, if we would have thought about this earlier, we could have recognized that M2 is going to be larger than M1 and that the final velocity of the projectile or the first object would have to be negative. It'd have to bounce back. But if we didn't recognize that, that is what our mathematics showed us in the end. Okay? So this problem now is completely finished. That is our last practice problem within the ideas of perfectly elastic collisions. What we're going to see next in our following videos are videos regarding collisions that are inelastic. Some work is being done or some energy is being lost. In general, we're still going to conserve momentum, but our energy equations, they change slightly. So until then, adios and take it easy.